Mitali, are you there? Okay. So Divyajyoti sir has joined? Yes.
Yes,
Okay.
sir.
Okay. Mitali, you can introduce Mr. Divyajyoti and the customer.
Yes, sir. Yes, sir. Sir, 1 minute now.
Yes, yes.
So, a very good afternoon to all of you present here. Welcoming Mr. Divyajyoti Panda sir, who has graciously accepted our invitation to join us today and enlighten with his knowledge. Now, requesting Sudeshna to tell more about sir. Sudeshna, are you here?
Sudeshna, are you there? Are you here? Sudeshna has not joined. Sudeshna is here though. Yes, yes. Yes.
I'm here, but I can't listen to anything. I can't hear anything.
Hey, you are audible. You are audible. Mitali, you just call Sudeshna. She is audible.
Yes, sir. Yes, sir.
I'm sorry for the interruption. I'd like to continue further. He completed his BTech from NIT Rourkela. He has worked in Oracle for a few years as a software engineer. His interest lies in algorithm design and machine learning. He has been working with NLP for quite a long time. He also builds software parts for robots for competitions and handles image processing, algorithm, and hardware aspects. So get ready for this insightful workshop, and I hope this is very educational for you. Thank you. I'll hand over it to you, sir.
Now, Divyajyoti, yours. Session is yours. You can. Thank you.
Okay. Am I perfectly audible and visible?
Yes, yes.
Okay. Okay, I'll share my screen. I'll ask everyone to let me know if everything is visible. I hope the slides are visible.
Yes,
Yes,
yes.
sir.
Visible.
Okay. So, good noon, everyone, and I welcome everyone to this Applied Python 2 workshop. And my name is Divyajyoti, and I am currently a student in University of Southern California. And I first of all thank Professor Satya sir and the organizing committee of this workshop and the KIT University to provide me this opportunity to be able to deliver a talk on in this workshop. I'll be delivering my talk on classification, clustering techniques, and implementation of ELM, where I'll be talking about a bit on a brief overview on classification and clustering techniques so as to give you a better idea upon what these techniques are. And along with it, I'll introduce you to very recent development on my neural networks, such as ELMs. I think it has been only a decade and a half or so when these have been developed, and these are fairly easy and you can take it to practice. So before I start, I'll tell a bit about me. So I am presently pursuing Masters in Computer Science in University of Southern California in United States. And I have also done my BTech in NIT Rourkela, as Sudeshna rightly pointed out. I have 4 months of experience at Oracle's as a software engineer, and feel free to reach out to me for anything right after the meet or the workshop through my LinkedIn, and I have given my LinkedIn in case anybody wants to reach out. And throughout this workshop, I would pause at certain points so as to take questions. You can ask me questions from the chat, or you can unmute yourself and ask me questions. So that everyone is on the same level and everyone understands everything. Okay. So with this, I'd like to start my my session. Okay. So let me tell what the agenda is. So first, I'll give you a very brief overview of machine learning, how what machine learning is. I'm sure you have already gone through what machine learning is through my fellow speakers in day one and beyond. But in any case, you feel any sort of lackings, I am ready to help you and answer your questions. Apart from this, I'll also cover a basic machine learning workflow, like what are the steps you need to cover while you do a machine learning project. We'll briefly discuss about what classification and clustering is. And at the end, we'll also talk about the buzzword, the big elephant in the room called deep learning and extreme learning machines, which the talk is all about. Throughout this throughout this session, I expect you to have a basic understanding of Python, as well as some familiarity on machine learning. If you do not have, that is also perfectly fine. You can ask me doubts. I am ready to help. Okay. So let's go through what machine learning is. So machine learning is the field of study that gives computers the capability to learn without being explicitly programmed. This is the definition given by Arthur Samuel, who is a very renowned American scientist and a pioneer in the field of machine learning. He has done a lot of work. So what exactly do we mean by this definition? So if you see traditional computer programs, you give it a set of instructions so as to how to achieve a certain task. For example, if you need to calculate the factorial of a number, which let's say 5 factorial is 5 into 4 into 3 into 2 into 1. I'll run a for loop saying that I give you a number, iterate from 1 to 5. I keep a product. I ask it to uh, run a for loop or a while loop or any loop. In that loop, I'll be giving you a set of procedural steps where I'm multiplying it continuously from 1 to that number, let's say 5 in this case, and I then achieve my result. So this is I am saying it to do what it has to do at each and every point of time. This is traditional learning or traditional computer systems. Whereas in machine learning, what we do is we do not tell it explicitly how do you program, right? So like for example, you tell the software, you tell your system that this is the set of data I have taken, and this should be the output, and you need to know how do I get the output. figure it out yourself. Then I give you new data and you find out new output. We'll see this later on. Okay. So this is what the core of machine learning is. So instead of telling it explicitly how to do it step by step, we are asking the system to actually learn from the data itself on its own, and we are making it capable enough to learn the patterns and then generalize it over new data. Now, we have 4 different types of machine learning approaches. We have something called supervised machine learning, unsupervised machine learning, semi-supervised machine learning, and reinforcement learning. So, supervised machine learning refers to the fact that you tell what your inputs are, you tell what your outputs are. You're training it on data which has both input and output. For example, you are giving a housing prices data set to your computer system, and you are telling it a bunch of factors, like for example, when was this built? What is the area of the plot? What things are built on this plot? What is the uh, purpose of the plot? What is the location? Is there any highway around? And I also give it an output called price. For example, for instance, what the price is. Now at the end, I give you, I ask you for another plot I have, and I ask you what the price is. This is supervised learning because I have given you a set of prices for the data which is given for training. Contrast this to unsupervised learning. For instance, I have given you a set of data, let's say news articles. Okay, so I have news articles based on, for instance, India renaming to Bharat, or we have for Lok Sabha elections or for state elections. And we also have for example, the Chandrayaan-3 mission to moon or something on those lines. So here we are not explicitly telling it to group it under political or scientific or anything such realms. We are just asking, take these bunch of news articles and make probably 3 or 4 clusters out of this. And in and the computer figures out, yeah, these things look similar, that's why they should come in the same cluster. These things look different, so they should come in a different cluster. So this is unsupervised because we do not give any output in the case of training data. Then we give it a data point and ask it that which cluster it belongs to. So this is unsupervised. Semi-supervised is basically that you have our entire data. Some of it has an output and some of it does not have an output. So, for instance, if you are doing image classification, for example, cat dog classification, it might happen that you have such a large data set, you could only manage to annotate a few images saying that this is a cat or dog, but the rest of the images you cannot figure out. You were not able to figure out whether it is a cat or dog manually. You ask a system that, yeah, I have these set of images. Out of this, a subset has been labeled as cat or dog. You tell me, you make a model yourself and can figure out what exactly you mean by a cat and a dog. That's a semi-supervised learning. Reinforcement learning is a different paradigm altogether. Reinforcement learning depends on a set of rewards and punishments. For example, I ask my system to for instance, I'm taking a problem statement saying I want to make a system who should learn a particular game, say chess. So I give it a board. I do not give it any rules how to play. I just say I give it some constraints. For example, you need to move from one square to another square. That's all I give. And I can also feed things like players should alternate among each other. And I may also give some basic moves, or I might decide not to. So the computer first gives me a move. I dis First of all, I see that move and decide whether that move is legal or not, whether that move is good or not. If it is a good move and it benefits the situation, I tell the computer, yeah, this is a beneficial move. Go with it. If it is not beneficial, or it is illegal, I ask the computer, no, you have done wrong. You have to go the other way. Through this series of interactions and feedbacks, I make the system actually learn what which path or which moves would actually be good for my system. This is what reinforcement learning is. So next, there are two major stages of making a machine learning model. There is training, there is prediction. Training means I have given it some data, training data, and the machine learning model or architecture is learning patterns and rules from input data. For instance, if I take the same cat and dog example anecdote, I give it some images and I say that this is a cat and this is a dog. And the model runs for some time, learning this pattern that, yeah, this is a cat and this is a dog. This is called training. Then after the model is trained, the second part which comes is prediction. So prediction says that now I have made you a model, like the computer has made me a model. I gave you a new image. Okay. Tell me whether this image is an image of a cat or it's an image of a dog. So now it is able to predict from whatever it has learned from the past that, yeah, it is a dog or it's a cat. So these are the two major stages of machine learning models. Does anybody have any sort of questions here till now? I'll pause for a moment for people.
No, sir.
Okay, fair.
Sir,
Then, yeah, go ahead.
can you please throw more light on semi-supervised learning again?
Semi-supervised, right? Okay, so semi-supervised learning actually means, for instance, I have given you a data set of images. These images consist of some of these images have been labeled as they are cats or dogs. For example, I'm giving you a wide range of images and of cats and dogs, and I feed it to a computer and I want to make it learn that whether it is a cat or a dog. But it's such a large data set. For example, for instance, it might be millions of images. I might have only be able to label only certain range of images which have that it can be a cat or it can be a dog. But for instance, for 10 million images, I only managed to do, for example, 1000 images saying that, yeah, this image is a cat or this image is a dog. Whereas for the remaining, I have just given it an image of a cat or dog. The computer does not know by itself that it is a cat or a dog. The computer is tasked to learn from this entire data set what exactly a cat or dog is. So you have a supervised realm where you have some images which tell you what cat or dog is. You also have an unsupervised realm which where you have just given the images and you haven't told the system what cat or dog is. So this is what semi-supervised learning is. How do we solve semi-supervised? There are various paradigms and various methods saying, like, for example, you can first train it on supervised, then use it to classify your entire unsupervised data set. Then you train on the entire data set with where every image has been labeled. So there are many methods of doing semi-supervised learning. I hope this answers your question.
Yes, sir. Thank you, sir.
Okay. Anyone else? Okay. I'll go ahead. So I'll tell you a basic workflow of how a machine learning project goes through. Okay. So I'm giving a workflow diagram. Take this with a grain of salt, because uh, this is something which how traditionally machine learning engineers used to look things at. But now the software life cycles and and all these things have developed so much that projects now go concurrently. Many of these things happen overlappingly one over the other. But I do want to give you some idea on how machine learning projects goes through. Okay. So there are three key parts of a project which involves machine learning. So we have one pre-building phase, we have a building phase, we have a post-building phase. So pre-building phase identifies is what typically uses like identifying use cases, or what your problem statement is, doing a literature survey, collecting data. So this is the pre-building phase. We have the building phase where we actually build the model, and we have the post-building phase where we actually we integrate this model to your system and then maintain it. Typically, the pre-building phase is handled by people like business analysts or statisticians or people who collect data and so on and so forth. The building phase is typically what ML engineers work on. The post-building phase is more typically a software engineer or DevOps engineer or someone on the or a tester or someone on the light works on. But many of these are now overlapping. So I'll shed a bit light on these. So yeah, what typically happens before you actually build a model? So first of all, you have a set of steps which I have identified here. Number one, you need to define your research problem. For instance, you let me consider the fact one particular case study where you are detecting whether a patient is having any risk of a heart disease or not. Let us consider this. Now, the research problem definition involves like uh, identifying that, yeah, I want to develop a system which is able to means detect whether a person is having heart disease or not. This also involves maybe allocating like analyzing the uh, benefits of the idea and whether this idea is viable to make a project or not. This is one of the crucial parts of making a project. Then once we have a clear idea of how the problem goes through, we go through a literature survey. And through the literature survey, I am identifying whether like is there any existing implementation or any existing thing which actually does the job or which is very similar. In many cases, our problem stops right here, because if we find something which is already working well enough for our job, we just go with it. In industry level, in academic level, in any level, But if we do not find anything, we formulate our problem statement. Now we develop it formally, saying that, yeah, I have these set of features. Like for instance, this is my blood pressure, this is my heart rate, this is my history of records of any history of heart disease. My family has these set of diseases in its history, and so on and so forth. I have given you this set of data, and you identify whether that person is in the risk of having a heart disease or not. This is a problem statement formulation. The difference between research problem definition and problem statement is in the viewpoint. So research problem definition is in the views of what a businessman would look like. For example, what is the overall definition of the problem, what I want to do? Like, I have to treat I have to check whether the person is having a risk of heart disease or not. How viable this this problem is? Can I allocate a sufficient number of resources or not? Is it beneficial financially for me, or is it beneficial for me to do this project or not? Things like this. On the other hand, when we do a problem statement, we are doing it from a developer's perspective, saying that, yeah, I'm giving you these set of features. I have to take these set of features, and I have this set of outputs available. Now I want to make a model saying that, yeah, I'm giving you things like history, BP, and all that stuff, and I give you and whether the person has having any risk of heart disease or not. Now I give you a new data point with again new set of a new history, BP, and other things like that. The model has to tell me whether this has a heart disease or not. So taking your problem definition down to last level is what problem statement formulation involves. Then we come out with research designing. So we have your problem in hand in great detail. Now you design how your experiment should go. Like how you collect data, how are you going to proceed? What are your steps going to be? What is the type of architecture you are going through? And how are you going to validate your results? Whether it be based on any pre-existing ones, or or how are you going to validate? Then we go through data collection, where you are collecting data from various sources, whether it be surveys, whether it be some online sources, and so on and so forth. All this is involved before you are building a machine learning model. Then we go through the building phase, where we are actually building the machine learning model. This is what is mostly crucial for us machine learning engineers. So number one, we have our data with us. We need to pre-process it so as to make it suitable for our task. For instance, I might be having ECG signals of patients. However, computer does not understand analog signals, right? You have to extract features like whether do you see a normal T wave, whether you see a normal shape. Do you see any abnormalities in the heartbeat? If you see an abnormalities in the heartbeat, what sort of abnormalities do you have in the heartbeat? So identifying things like this comes under feature extraction, which is a part of data processing. What else do we have? We can also be looking at some data where you have some missing values. There might be that data was not available or it was not correctly recorded, so it is missing. So there might also be things like outliers which you would like to treat, things which are like data points which do not seem to be within the range. For instance, typical BP ranges between, like, for instance, a normal BP is 120 by 80. We can have 160 by 40 or something like that, but we cannot have a BP of systolic pressure down outright to 400 or 500 or something. So things like this also need to be treated in our data. This is crucial. This is what comes in data preprocessing. Number two comes is feature importance and selection. And many of the models do go through this step. Many of the models also skip this step and go through training. So we have a set of features, let's say family history, your history of heart diseases. Maybe you might have also collected things like temperature or any other sort of diseases like COVID or lung cancer or lung diseases and any sort of things. You also need to figure out whether all of these are actually relevant for your study or not. So some of this can be found out through domain knowledge. Let's say studying and let's say deciding, for instance, that you in for your particular disease which you are talking about, maybe your family history may or may not be a very important factor in deciding whether do you have a disease or not. Things like this can be done out of domain knowledge. Sometimes you cannot we do not have sufficient domain knowledge, or it is not available for your knowledge that these features are actually irrelevant or they are irrelevant. In those cases, we do have certain machine learning frameworks and statistical frameworks which uh, do find it out for your given data set whether this feature actually predict is used instrumental in predicting your outcome, or is it actually irrelevant, number one. Or number two, if for instance there are two features which are very much dependent on one another, you can use only one of them for predicting your target. You do not have the other one. So dropping features like this is crucial because it reduces our time and complexity of the model. This is what is covered by feature importance and selection. Third is training. So we train a model, whether it be any sort of model we try to train, whether it be a classification model, whether it be a regression model, and so on and so forth. We are training the model on the training data set. Fourth, prediction. Prediction involves finding out the output for your new test data, which you have kept for testing what your machine learning data is, like how your machine learning is working. Fifth, evaluation. So you have, for instance, you have taken 10 new patients, you have classified whether they have heart diseases or not, and you might be having some ground truth saying that, yeah, these are actually having risks, or these were actually not having risks. Now we compare these two sets, whether they actually what the machine says and what they actually had. And you compare this and you find out a metric, for example, accuracy, how accurate your predictions were, whether was it able to correctly figure out is if there is a difference between and like if there is a difference between the two, or is it able to correctly point out if there is a heart disease, if there was a heart disease in the first place. So things like that. At last, we come to validation, where we are checking the significance of the results. So, for instance, if you are comparing two models, it might be two models of your own, or it might be a model under any other literature survey, one you found in the literature survey. which does a similar same thing, and you compare, is my model significantly better than this the other model or not? If it is not significantly better than the other model, then it's better as well just to go with the one which is tried and tested, as opposed to testing and taking your own model which you have developed from scratch or you have just developed. But if your model is actually significantly better than the other model, then it is better to go, then you can go with your own model. Many of the machine learning projects are many of the machine learning research do not do this step, but it is very much essential for your own research. After this, we have very important, after your model is built, we have things like documentation, like developing a manual for users to how to use the model. We have application integration, like how do you actually integrate your model with your own software from with the backend or front end to identify how your model is going to interact. Then testing how your entire software is working, if your software is working or not. Then we actually deploy and release it to the public, saying, yeah, this is my app. You can go through, you can use this app and log in and give your data. It will be telling you what your output is. And at last, we also have maintenance, where you are you're updating your software, you're fixing bugs. Oftentimes, in this last step, maintenance is the genesis point for the workflow to repeat. If you find, yeah, this machine learning model is not able to account for this feature, or your software has this problem, you may repeat through the workflow all over again, doing the same set of things to make your things better. So this is a cyclical way of developing your machine learning models, and as you progress, you make your model and your software better and better. Okay. So nowadays it is not linearly fashioned, saying that, yeah, you have to complete a machine learning model, then it will be integrated with the software, things like that. Sometimes in a big system, or in where you have multiple machine learning models or something like that, many of these things can actually go in parallel. For example, you might be building a machine learning model and you are still developing a documentation along with it, or things like you are developing your data, as you are taking your data, you are collecting your data, you are using your existing data which you have already collected to make your model, and then you are working on improving it with ever increasing data coming in. So the many things are overlapping, but this is a general structure of how machine learning project goes through. With this, I'll pause once again for any questions anyone has in this section. Does anyone have any questions?
I think no, you can continue.
I see something. Okay, no.
No.
Okay, okay. I'll go with classification then. Now, as we have already seen how you actually do machine learning projects, now we will go in more detail as to how we'll pick one particular paradigm and we'll see how classification works. So what classification is? Classification is identifying the category of new data points based on your training data. For instance, the problem statement I had taken for cat and dog. You have a set of images and you have you have given labels or outputs for these images, that, yeah, this is an image of a cat, this is an image of a dog. I give my model loads and loads of data, giving details on that. Now I am giving it a new image, say, and I am asking it to actually identify whether it is a cat or dog. This is a classification model. Now, a classification model can be of multiple types. It can be binary, for example, a cat or a dog. It can be multi-class, like it can consist of more than 2 classes. For instance, what sort of an animal is it? Is it a cat? Is it a dog? Is it an elephant? Is it a lion or something on those lines? Or for example, I have given you a set of like characters. If in case of OCR recognition, does this character correspond to A, or is corresponds to F, or is it corresponding to H? Things like this. So this counts as multi-class classification. Can classification be unary? Answer turns out to be yes, but it may be in it being supervised may be debated. So how classification can be unary? How do you classify into one class? For instance, the training data only contains things like consider a factory line where you have a set of pipes which are being manufactured, and I have given you a set of features for those pipes, saying that like all these set of pipes are normal, and I have I have these set of features which are for the pipe. For instance, this is my tensile strength, this is my diameter of the pipe, this is uh, how much stress it can handle. So in what temperature does it melt, things like this. So the only data I'm giving it is of pipes which are having normal behavior. This is all I give. Now I give it a new pipe. The model has learned only on this normal set of pipes. I give the model a new pipe, giving it a set of features, and I ask the computer, is the pipe normal or is it not normal? So if this pipe is not significantly different from the other any of the other pipes which it has identified, then you classify this pipe as normal. But if you find it significantly different from the other pipes, then you classify this pipe as abnormal. So you actually have only one class and that the pipe is normal. But the model is now able is figuring out whether the candidate pipe can be placed under this category or it cannot be placed in this category. So this now why people debate whether this is supervised or not, because this is as good as saying you have a set of data points, you have set of data points with corresponding to these pipes. You have another data point. Do you add, is this significantly close to these data points or not? So if you consider in this paradigm, I am not even considering any sort of input for classes at all. So some people, and most of the people do say this is unsupervised, but there are some cases where people do say that this is one class classification. This is the building block for anomaly detection. Now, on the right, you can see a figure, for instance, of one class classification for which I give an example of. This might be a set of normal pipes. This minus is something which might be considered abnormal because they are not significantly close to other pipes. On the other hand, you have multi-class classification where you have set of normal and like set of attacks, and you are trying to segregate different types of attacks from normal observations. Therefore, I am classifying it to multiple classes. Now, what can be some applications? So, number one, you can go through spam classification more. So I'm giving you certain emails or something on those lines. Then I identify whether this email is actually a spam mail or is it not a spam mail. Things like this. We can go through sentiment analysis as well. So whether I'm giving you a set of tweets, you have to tell me whether this tweet is actually using abusive language or not. Is it written in anger and is it aiming to spread hate or not? Things like that. So that identifies a sentiment analysis. We can also have disease risk classification. For instance, I'm giving you a set of features and I have given you an output. Whether that person is in the risk of having the disease or is it already having the disease or not. And I'm giving you new data points. You have to tell for those data points whether that whether that person is going to have the disease or is having the disease or not. We also have object detection. For example, I have given you an image. What I gave for cats or dogs. So I have given you images of cats or dogs. You have to identify whether that image is of a cat or that if that image is of a dog. This this can be generalized to say, for example, I have given you an image. You have to identify what the where your cat is and where your dog is in the image. So things like this, where we build one on top of the other, is something which is very much prevalent in machine learning paradigms. This is what object detection is. Voice recognition. For instance, this is my voice. You have recorded me, my voice, and then you have recorded somebody else's voice. You now uh, give your system a set of voices along with the person, people who are speaking, uh, like who has spoken, whether I have spoken or somebody else has spoken, and I feed it to a computer. Now I give it a new recording and it identifies who is the person who has spoken that. So this counts as voice recognition. You might be having even more complex applications of this. For instance, I'm giving you a recording. You have to classify and identify what is the language which the audio is being spoken, whether it is being told in English or Spanish or Hindi or Odia or Portuguese or any language. So these are some applications of classification. Now we have two types of classification algorithms. We have lazy learner classifications and we have eager learner classifications. Lazy now this these two types of classification actually come through the thing I have discussed earlier. There are two phases of building a model. There is a training phase, there is a prediction phase. Where are you these two types come from the fact that where you are doing the most heavy lifting work. Are you doing the heavy lifting work when you are training, or are you doing the heavy lifting work when you are predicting? So if you are doing heavy lifting work in case of predicting, this is called lazy learner classification. And this requires minimal pre-computation, but for each data point, you have to learn again, you have to do the same work again and again. For example, KNN. If I tell you what KNN is, I have given a set of data points to the model. For instance, um, identifying whether that model is a cat or a dog. I have given it a set of data points in n-dimensional space. For simplicity, I'll just identify two-dimensional space, for instance. Let me just draw. Um, so let me consider a two-dimensional space like this. And I have these points which say that this is a cat in these two features, and I have these points which say, yeah, these points correspond to what a dog looks like. Okay. It might be even overlapping in this regard. So I might be having points like this, for instance. So your now I have a new data point, let's say here. Now I want to figure out whether this image is a cat or a dog. So what I'll do, for instance, I consider k nearest neighbor. So let's say my k is equal to 3. Okay. So I take my 3 nearest neighbors. If you can, for an instance, this might be my 3 nearest neighbors. Now there is one picture which is labeled as cat, and 2 pictures which are labeled as dogs. Now in this scenario, what I'm going to say is, since my image is mostly close to images of dogs, my image is more likely to be a dog. If it would have been a scenario like this, then it is more closer to images which are cats. So I classify this image as a cat. This is what KNN is. Now, if you notice, while I'm training, I'm actually just giving it data points, and it keeps in mind where the data point is. It does not do any pre-computation. But in case of prediction, when I'm giving you a data point, it actually calculates what is the distance with other data points which are close to it, and it identifies whether which neighbor is close to it and whether it is a cat or dog. So most of the heavy lifting has been done here. Therefore, this is a lazy learner classifier. On the other hand, we have eager learner classifiers where most of the heavy weight work has been done in training phase. Learning whether the model is actually doing like a cat or a dog in the training phase itself, instead of doing it at the point of like classifying. So um, let us take a example of a decision tree. What a decision tree is, it is basically a set of decisions which the computer figures out whether that picture has whiskers or not, whether that picture has pointy ears or not, things like this. So if it has whiskers, it is more likely that this is a cat. If it has pointed ears, it is more likely that it is a dog. If it has, let's say, grayish eyes with very pointed looking like pointed eyes, it is more likely to be a cat than to be a dog. So we are giving this information of images of cat and dog with the labels. The computer or the system identifies these set of features and tells whether this is a cat, whether it is a cat or a dog, and what set of rules it is going to go through. Once it figures out this, then we give it a new data point, and it figures out automatically where the cat or dog lies. So here, most of the heavy lifting work has been done in the training phase, where it figures out the rules. Once we give it a new data point, it has nothing much to do. So this is something which comes in eager learner classification. Okay. I'll quickly move on to clustering before I take some doubts. Now, classification and clustering are very related paradigms. Clustering comes under unsupervised learning, whereas classification comes in supervised learning. In classification, you are let's say, given images of cats and dogs, and we were actually telling what that image is of a cat or that image is of a dog. But now in case of clustering, we are giving it a set of data points, and we do not know how any outputs or any labels of these data points. I just cluster it into a set of groups called clusters, such that the points which are close to each other in the feature space lie in the same cluster, and the ones who are further apart lie in different clusters. That is the sole difference between classification and clustering. Now you have different types of clustering algorithms. You have centroid-based clustering, which is what I told about. There is density-based clustering. For instance, the points where the areas where the points are much more close together must come in the same cluster. Where they are more further apart, they do not lie in any cluster, or they belong to different clusters. We also have hierarchical clustering. So, for instance, if we we have one cluster, that cluster has two more clusters, and that cluster might have multiple more clusters, and so on and so forth. Um, the applications of clustering can be recommender system. Hello? Um, okay. So applications of clustering involves, for instance, number one, recommender systems, where you are identifying you have a set of users and their preferences for, let's say, films. So you are identifying, for instance, a set of users who have very similar preferences of films. In this case, I have not told which user is in which class, but I just have a set of features that, yeah, this person A is watching this film, person B is watching that film. I identify that person A and person B are very similar in their taste. So whatever person B likes is recommended to person A. So this is one example in which recommender systems use clustering. Customer segmentation is likewise very similar. So, for instance, customer segmentation can be that I have given you a lot of customers. I have to deal with these customers. Instead of dealing with each customer like individually, it is better if I group them into several different groups and I cater to each group. But in many of these cases, I do not know in which group these lie on. So I might have a set of features. I I group them into certain clusters, let's say 5 clusters or 6 clusters. I notice the common features in those clusters and I cater them accordingly. So this is customer segmentation. Search result clustering. So I might Google or any other search engine might return you a lot of search results. So things like whether if these two links or these two websites are similar in nature. For example, if they have similar content, or if people go to the same website after going through these two websites, or things like that, then these can be grouped together, and and it is very much useful in case of processing search results, as it makes it things faster. Then we have social network analysis. So people who are more similar in respects, for example, if they go to the same university, or if they are working in the same company, or if they have more mutual friends, they are more likely to be knowing each other. So recommending algorithms recommend them as to be your potential friends in your friends list. This comes in social network analysis. image segmentation. For instance, you have an image which consists of let's say flowers. You have to detect the flowers in the image. So if I consider, for instance, a particular a scenery with, and you have to identify flowers, it instead of going pixel by pixel, it is often useful to see whether and those pixels which have similar colors. So for instance, if I am considering pixels which are green in color, it is more likely that it is not a flower. In case of, for example, roses, if I find pixels which are red in color, it is more likely to be a part of a rose. So things like this, it is actually better to, instead of going pixel by pixel, it is better to classify them into clusters or group them into clusters and then identify, yeah, these set of pixels do not take part in any flower, but these pixels are actually corresponding to pixels of a flower. So this is how image segmentation uses clustering. So as I've already highlighted, the difference between classification and clustering. So classification is a supervised algorithm, whereas clustering is unsupervised. And classification groups instances based on labels, but clustering identifies groups and groups instances based on similarity. Okay, with this, I'll like to wait for if anybody has any questions here. Does anybody have any questions?
Yes, sir.
Yeah, go ahead.
Yes, Subi, you can ask.
So when you talked about clustering, you talked about centroid-based clustering, density-based clustering, and hierarchical clustering. So where do algorithms like k-means fall here? K-means clustering.
Okay, k-means clustering actually falls under centroid-based clustering. So if I give an example, what k-means clustering is, I have these set of data points. Okay, I have, for instance, I have identified 3 random points as my centroids. I find out what is the what are the which points are closest to this centroid, and this centroid. So it might be this group. Let me use another color. So it might be then this group, and it might be then this group, on something on those lines. Now I then calculate the mean area of these. So I might consider this point now, and this point, and this point. So, and now I update my centroids to my new locations. You can start from random points. You can also even take points which are existing data points. Now, as you can, sorry, this actually went here. I started from here. I actually went here. Now I can, okay. Now I can see, for instance, in this case, my data point is actually going closer to this cluster. Okay, this actually went away. So this went to this cluster, this is going away from this cluster, and this is approaching this cluster. So if you repeat it in a couple of steps, this point is going to come here, this point is going to come here, this point is going to come here, and your clusters are identified as this, and this. This is what centroid, this is the property of a centroid-based clustering, which K means comes under. As an example, for density-based clustering, we have something called, let me see. Okay. We have something called DB scan, which is a typical density-based clustering algorithm. And for hierarchical clustering, we have several algorithms. We use something called dendrograms, which are useful for hierarchical clustering. Does this answer your question?
Yes, sir. So if I've understood, does that mean under centroid-based clustering, we have algorithms under it, and like under each category you've given here, is there another? Okay, under that, do we have more? How shall I term it? Like subclasses under it. The way you said K means falls under centroid. So does that mean under density based we have algorithms under that, and under hierarchical clustering we have algorithms, like examples under that?
Yeah.
Okay. Another question.
Okay.
When you talk about class supervised learning, so we
Okay.
looked at classification. So
Okay.
I've I've ever heard about regression. So does that come under here, or that is another topic?
Regression is another topic. So, for instance, what happens in regression is I'm not classifying it into classes, but I'm assigning some value to it. For instance, the example which I had taken initially regarding housing prices data set, where I have given you a set of features regarding what type of plot I have and what type of construction has been done, and then identify the price of the price of the plot. So in this is an example of regression where I'm not identifying any sort of classes between where this plot lies, but I instead actually like just give it a price tag, which is a numerical value. It's not a category. But in case of classification, we are assigning categories. For instance, whether it is a cat or if it is a dog, something on those lines.
Oh,
Does this
so regression only deals with numerical data, not categorical data.
The features may be numerical or categorical, but the label or the output which I'm assigning it to is numerical in case of regression, and it is categorical in case of classification.
Oh, okay, so does that mean if I have if my data frame has both numerical and categorical values, if
Hmm.
I'm to use any regression algorithm, should I make sure that I change all the values into a numerical data?
No, let me make this clear. So I just now said if my label or output, whatever you might call it, if that is numerical, that falls under regression. If that is categorical, then it falls under classification. For instance, if I consider the housing prices data or some data on plots, there might be some categorical data. For instance, is this plot close to a highway or not? This is a yes or no question. This actually falls under categories where some plots come under the category yes, and some plots come under the category no. I'm not like whether it is a regression problem or a classification problem has nothing to do with the features. It has to do with the output which I'm dealing with. In case of housing prices, I'm dealing with prices, which is the price of a plot is a numerical data. Therefore, it falls under regression. In case of cats or dog example, my output is whether the image is of a cat or a dog. This is identifying into classes. So therefore, this is a classification problem.
Okay, thank you, sir.
Okay.
Sir, I had a question.
Yeah.
Sir, you talked about a topic related to data set. So, how do we decide that how we have to divide the data set into the training data set and a test data set, like percentage, like 50-50, 60-40, 80-20? How do we decide?
This actually depends on your domain. So, for instance, sometimes you might not be required to actually divide because you might decide that, yeah, that whatever data will come new or will be data collected later might be your test data set, and right now it is training, and whatever I have is training. Sometimes I might require to divide it into train and test data set. So in this case, it is better to actually experiment with multiple scenarios, whether a 70-30 is useful or 60-40 is useful or something on those lines. Whichever actually gives you the better division is actually is going to be useful, is going to be your way to go. Um, for those purposes, we also use something called validation dataset. So we actually, first of all, we check whether these multiple models are which one is better through another division from validation. Then we test the entire accuracy or entire the metric of the models in and through the test data set. But coming back to your question, this is up to, and like number one, this is for your from domain knowledge, like how much data you should keep for train and test, how what people have taken. Because if somebody has taken a particular data set and it has been split into train and test, and if you want to compare with that model, it is better to take that train and test which they have taken instead of taking off your own. Then only it is fair to compare. Number two, if you taking that aside, it is better to actually experiment with what train and test you are coming up with, because at the end of the day, it's the accuracy or the metric on the model which we are concerned with. Okay.
Yes, sir. Yes, sir. And one more question, just related to the reports, like how long we have to run the tests on the data set. Like it also depend on the accuracy. It's sometimes given criteria, like we have to reach a certain level and then we have to stop.
Okay, so this is a question which is pertaining to deep learning, I think. So I think you're referring to the fact that whether how many times do you need to run your model?
Yes, sir.
And
Yes, sir.
okay, so yeah, so in this respect, there are different, again, there are different uh, criteria. In some scenarios, we have your threshold accuracy if or threshold error. If you cross this limit, then my model is good enough, I'll stop. There is one you can do in this respect, or you can do in this or you can do with the fact that I'll let it run continuously until it does not change beyond a particular threshold. So if after running for, let's say, 50 or 100 epochs, if it does
Yes, sir.
not if it does not change within beyond a 0.1 accuracy or 0.1 error, I'll stop. There might be this. It can also be things like if it is not varying too much. So if I am recording variance from the start, then it is like when it starts stagnating, then I'll stop. It might all like there are multiple things which can happen here. I might also just run it for, let's say, 100 iterations and then I just stop because I don't have much time to train. So yeah.
Thank you, sir.
Okay. Okay. Anybody else? Okay. Fair. I'll quickly go to the remaining slides. I have to complete a lot. So let's go to deep learning and ELMs. Okay. I'll go pretty quickly in this respect. So deep learning is using neural networks to train models. What neural networks are, we actually we have an interconnected layered network of nodes on neurons. If I want to give you an example of this for example is can be classified as a neural network where you have inputs, you have outputs, and you have weights and biases assigned. So if you have for an whatever comes here, we go through a certain transformation, which we'll go through later on. This transformation and the data is transformed and it is given to the subsequent layers. And at the end, we are trying to fit it to the output. Now, this how close we can go to the output depends on the weights and biases, and we are trying to tune it accordingly so that we have minimal, like we are as close to the output as possible. So this is what deep learning is. Now we have different types of deep learning architectures. We have artificial neural networks, we have extreme learning machines, we have recurrent neural networks, we have convolutional neural networks, etc. So let me talk about extreme learning machines pretty quick. So it was proposed in 2006 by these scientists, Guangbin, Quinzu, Yuzu, and this in the paper Extreme Learning Machines. And it was proposed, but the ideas of this were pre-existing back then. It is just that these scientists and these researchers have formalized it into one domain called extreme learning machines. This is a feed-forward neural network with one hidden layer. So if I will give you an example, what this an architecture would look like. Feed forward means that it always goes from one layer to another next layer. It does not go back. It does not go back to the previous layer, or it does not go to the same layer. It always goes to the next layer, and we only have one hidden input layer as input in the architecture. We have an input layer as usual, we have an output layer as usual. Now, this is a very interesting part. We actually, this is one neural network where you do not need any backpropagation. So you do not need to actually develop, uh, means update any weights here. Once you have to run it just once and you're done. This is something which makes your extreme learning machines very attractive for researchers, because you have to just run it once. Now, because now it uses simple matrix manipulations to train. So it is faster than conventional neural networks, because instead of doing like going through it multiple times through multiple epochs when the like updating my weights and biases accordingly, instead of that, I just take it through one iteration. I find what my optimal weights and biases are, and then I identify whether like I am done with my model, which gives me results whether this model is actually you uh, able to classify my data correctly or not. Now, let me give some basis on how this model works. So consider X as an input matrix. W1 is the weight matrix in this side between input layer and hidden layer. W2 is my weights vector between hidden layer and output layer in this region. I'm also including biases in my weights. sorry, this should be output vector. Please disregard this. Y is my output vector, and let sigma be my activation function. Now, considering this, we can say that y is equal to W2 into sigma W1x. So this is in the matrix matrix paradigm. You can model any machine and like deep learning or neural network in this respect. So y is equal to W2 sigma W1x. This is for single input hidden layer. In this case, I want to point out my activation function here is just linear. I actually do not have any activation function in case of my hidden layer to output. I just have activation function between my input to hidden layer. That is why you can see only one sigma here. Therefore, y is just W2 sigma W1x. Now, it will if I want to change my subject of the equation to W2, I would like to take this to the left side. So it will be useful to do an inverse. But the problem is sigma W1x is actually the vector which gives you the output of this layer, hidden layer. Like input to the hidden layer, but I cannot invert it directly because it is a rectangular matrix. A rectangular matrix does not have any inverse. So I am doing a set of operations. So here, if I change this to left hand and I take this to right hand side, then I multiply the transpose of this matrix on both sides. What does this do? Consider, for example, I have this rectangular matrix of M cross N, okay? And I transpose it, I make another matrix called N of N cross M, okay? I multiply these two matrices. Now I come up with the resultant is an M cross M matrix, okay? Now, M cross M matrix is a square matrix. Now, this square matrix can be invertible. So, this entire thing can now be inverted. Therefore, I multiply the inverses on both sides. Now, something multiplied by its inverse gets cancelled, and I multiply the inverses here. Now, if my W1 is known, let's say by some miracle W1 is known, X is known, Y is known, my activation function I have already decided on my own behalf. I can calculate W2 from this entire equation. So W2 comes out through this big formula. Now, this term sigma transpose W1x into this is termed as a Moore-Penrose pseudo-inverse of sigma W1x. This is a special way to do an inverse in case of a rectangular matrix. Okay. Now the question arises, how do I start initialize what my W1 is? So what ELM works is, it is fairly simple. You just randomly initialize W1, then you compute W2 with the given formula. So you just calculate W2 with this. So now the only thing which you need to change or you need to think of is the activation function. You can do sigmoid, you can do hyperbolic tan, you can do ReLU, anything of those lines. You can vary your activation function and see whether you are getting good accuracy or not. Now, as you can see, I did not require any back propagation or any sort of updates. You just did it once and you are done. The disadvantage of this though is you are concerned with a lot of matrix multiplications. So you actually need a lot of space to be able to do these matrix multiplication in your GPU. If you have a really large data set, for instance, if your X and Y are extremely high dimensional or extremely large, then your matrix multiplications will take enormous amounts of space, which might be which might not be viable in case of training in your GPU. So as a demonstration, I'll take a UCI cardiotocography data set which predicts heart disease in fetuses. I've taken 297 instances out of 2126, which has no null values. These are a set, it has 21 features. I have taken, and these are some features which it has. And it has two labels or outputs. It has a class output, it has an NSP output. I am taking the NSP output. It says whether the heartbeat, whether the patient is normal, if it is at risk, or if it is actually having a disease. So if I want to implement ELMs, I import my libraries. So I import NumPy, Pandas, sklearn. I also import time just to check how much time it takes. So I import a data set. I define my activation function. This is I have taken sigmoid activation function in this case. I do a train test split of 0.2. So 20% is taken as train as my test, and the rest 80% is taken as train. Then I just initialize some variables. This is initializing your W1. So I just do it I just sample it from a normal distribution. I do this is my main ELM implementation, which calculates W out, which is W2 from the formula I have given. This is the formula I had illustrated. Then I use it to predict it for new test data set. After this, I have this was, since I had shown that this was a multi-class classification where with normal, suspect, and pathologic, I took pathologic as my positive and rest as negative. So this is converting it to binary classification. This generates, this is the code which is used to generate confusion matrix. You can also use corresponding sklearn outputs. This is used to generate multi-confusion matrix. This is used to threshold your values, because at the end of the day, what it is it is a set of matrix operations. So the output of matrix operations is going to result in real values of y. Now in order to convert these real values to classes, it is better to threshold. So if my output is 2.5 or greater, I will classify it as pathologic. If it is between 1.5 to 2.5, then I'll classify it with 2, and so on and so forth. This is generating matrices, metrics. So I have calculated different metrics on this. So as you can see, in this particular implementation, I am already getting an accuracy of 82% on this data set, which is very significant, considering I have done nothing in respect of feature selection or which features to take or not. And the time taken is also in within 1 second, which involves both training and prediction. So therefore, this illustrates how significant an ELM implementation can be. So thank you everyone. Feel free to reach out to me in case of any if you want to discuss further or anything. I'm also attaching my LinkedIn profile in case anyone wants to reach out. With this, anybody wants to ask any other questions before we end the session on ELMs or deep learning?
Thanks, Divya. Such a nice session. Anyone having any questions? You can ask now.
Yes, sir.
Yeah,
Yes,
go
Subi.
ahead.
Thank you, sir. So it's amazing how ALM uses only one iteration and there's no feedback propagation. So what factors should you consider to choose this? Does it depend on the number of layers you're having, or is there any factor you should consider before you choose to use it?
Okay, so number one, ELM only uses one layer. If you had multiple layers, then the problem with this approach is if you this analysis doing it for just one layer, you you can all you are only able to calculate W2 given any other thing is known. So traditional ELMs only use one layer due to this respect. If you are taking multiple layers, for instance, you would be required to randomly initialize almost all weights except one at the end, and then only you will be able to calculate the that weights from with respect to the other layers. If you are aiming for um more like if you are aiming for more optimal results uh, where you have better accuracy with all weights optimal, you actually have to go through backpropagation and make it go through the traditional paradigms. This is so ELMs are pretty fast and they give pretty good accuracies. But if you want to get more optimal, better accuracies, you have to go through traditional neural networks, which take more time and actually go and do the pain to arrive at the optimal solution. This is number one. Number two is I also pointed out that ELMs take a lot of space due to matrix multiplication. So if your data set is large, maybe ELMs might not be a good option unless you do some workarounds like batch size or something like that. So yeah, I hope this answers your question.
Yes, sir. Thank you.
Yeah.
Any
Anybody
more
else?
questions? Now over to Mitali. Mitali, are you there?
Yes, sir.
Okay. So
Thank you, Divyajyoti Panda sir. This was an amazing session. And sir, Satya sir, I have sent the feedback link.
yes.
Chat.
Okay, thanks, Divyajyoti. If anyone interested to do some collaborative work with her, then definitely I will contact. Thank you. So we are now ending the session. Thank you.
Thank you so much.